Hello, future engineers. Welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired, and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe. Level 74, as a round log passes through a sawmill, two slabs are cut off, resulting in the cross-section shown. Calculate the moment of inertia with respect to the x-axis of the cross-section if h is r over 2. What is the percentage reduction in Ix caused by the sewing operation? So here is the given figure. For this cross-section here, let's compute the moment of inertia with respect to the x-axis. And from there, we compute the percentage reduction in Ix as moment of inertia of this whole circle cross-sectional area here, which is pi over 4r to the fourth, minus the moment of inertia of the remaining section with respect to the x-axis, and divided by the moment of inertia of the whole circle, which is pi over 4r to the fourth, then times 100%. So that's the percentage reduction. So let's have horizontal strip for our solution, and the length of the strip is x, distance from this axis here, y, and the distance of the strip from the x-axis is y, and the thickness is dy as shown. And take note that this is the radius r, so that the relationship among x, y, and r would be by Pythagoras theorem, x squared plus y squared equals r squared. So differential Ix therefore is 4 times the moment of inertia of this differential elemental uh, figure from the x-axis, which is distance squared y squared times differential area x dy. So differential Ix is 4 times distance squared y squared differential area x dy. So that's the differential Ix, then multiply by 4 because there are 4 identical figures. Then the variable is y, so x is, by Pythagoras theorem, x is square root of r squared, this is r, big R squared, minus y squared. So differential Ix is 4 times y squared square root of big R squared minus y squared dy. So with our experience from calculus, we put the variable y equals r sine theta. So Ix therefore equals 4 times integral from 0 to h, and h is r over 2 of y squared square root of quantity r squared minus y squared dy. So we put the variable y r sine theta from our experience, also with the preceding examples. Then let's have a right triangle defining y equals r sine theta. So this is y, opposite r hypotenuse. Then this is square root of r squared minus y squared, which is also r cosine theta from the figure. Now, the limits would be changed. So from, if y is 0, sine theta is 0 over r, so 0, arc sine of 0 is 0. So this remains 0. Then when y is r over 2, r over 2 equals r sine theta, so sine theta is 1 half. Theta therefore is arc sine of 1 half, and arc sine of 1 half is 30 degrees or pi over 6. So dy is r cosine theta differential theta from here, differential. So Ix therefore is equal to 4 times integral 0 to pi over 6 of y, which is r sine theta quantity square. This is r cosine theta, and dy is also r cosine theta d theta. So Ix is 4 times r to the fourth integral from 0 to pi over 6 of sine theta cosine theta quantity squared differential theta. From trigonometry, sine theta cosine theta is sine 2 theta over 2. So Ix is 4r to the fourth integral 0 to pi over 6 of sine 2 theta over 2 quantity square differential theta. So This is sine square of 2 theta over 4. We can cancel 4. And from trigonometry, sine square 2 theta is equal to 1 minus cosine of 4 theta all over 2. So Ix is r to the fourth integral 0 to pi over 6 of quantity 1 minus cosine 4 theta over 2 d theta. So that's the identity for sine square of 2 theta. So integrating, Ix is r to the fourth over 2. So theta minus sine 2 theta, 4 theta over 4. The integral of cosine 4 theta is sine 4 theta over 4 from 0 to pi over 6. So I sub x is r to the fourth over 2 quantity pi over 6 minus sine of 4 times pi over 6, which is 2/3 pi or 120 degrees over 4. So sine of 2/3 pi or 120 degrees is square root of 3 over 2, then divide by 4. So this is square root of 3 over 8. For the lower limit, it is 0. Sine of 0 is also 0, so don't mind. So Ix equals r to the fourth over 2 quantity pi over 6 minus square root of 3 over 8, which is, if approximated or using in this expressing in decimal form, that is 0.1535 of r to the fourth. So for the percentage reduction, therefore, percent reduction is 100%. Quantity pi over 4r to the fourth minus 0.1535 r to the fourth divided by pi over 4r to the fourth. So using the calculator, the percent reduction in Ix is about 80.46%. Level 75. Determine the moments of inertia of the shaded area about the x and y axis. Also determine the polar moment of inertia about point O. So here is the given figure. So for our solution, we will call this alpha. And we have a formula developed or derived from the preceding videos that I have uploaded in YouTube. So this is alpha and that is alpha, and this sector here is oriented horizontally, and the formulas where this is the x-axis if this sector is oriented horizontally as shown. So by the way, tangent of alpha is 0.6 h over h. So tangent alpha is 0.6, alpha is arctan of 0.6, and that is 30.964 degrees, or in radians times pi over 180, that's 0.5404 radians. So the sector, the orientation of the sector is in this manner, and this is the x-axis, which happens to be the y-axis in this orientation, and the y-axis is the x-axis in this orientation. So Ix is equal to r to the fourth over 8 quantity 2 alpha minus sine of 2 alpha, if you can recall or remember. And Iy, so with respect to this axis, Iy is r to the fourth over 8 quantity 2 alpha plus sine of 2 alpha. So you look at the derivation of this for these moments of inertia with respect to x and y axis, and on this orientation of the sector in the preceding slide, in the preceding videos that I have still on moments of inertia. So as I said, the x-axis here for the sector is actually the y-axis if you look at the orientation. So we use this formula here. So therefore, the moment of inertia of this shaded area with respect to the x-axis is moment of inertia of this triangle times 2, and the formula is b base height cubed, where the base is 0.6 for this triangle, base height cubed over 4, if you can recall, then multiplied by 2 because we have two identical triangles, then minus the moment of inertia of this sector with respect to the x-axis, which is moment of inertia of this sector for this orientation with respect to the y-axis. So minus Iy of the sector. So Ix is equal to 2 times Ix of triangle. For the triangle, the formula for moment of inertia with respect to this axis and through the vertex of the triangle, also derived in the previous videos here, is base, which is 0.68, height cube over 4. So, and Iy of sector, so we use this formula because this x-axis is this y-axis for this orientation. So Ix is equal to 2 times 0.6h times h cube over 4 minus 0.75h to the fourth, that's the radius, 0.75h to the fourth over 8, then quantity 2 times alpha, 2 times 0.5404 radians plus 2 sine plus sine of 2 times 30.964 degrees. So if your calculator is in the radian mode, then you can have here 0.5404. If your calculator is in the degree mode, then you just uh, follow this substitution of the angle alpha. So the first term is equal to 0.3 h to the fourth. The second is 0.07764 h to the fourth. So Ix is equal to 0.2224 h to the fourth. Likewise, moment of inertia of the shaded section with respect to the y-axis is 2 times moment of inertia of this triangle, which is 0.6h quantity cube times height over 12, because this is with respect to the leg, and times 2 because we have two triangles, minus, so this axis here, if we look at and analyze this orientation here, is actually this axis is the x-axis. So you just flip the figure. So take note, this axis here is this axis here. So this is y-axis for this guide. So therefore, Iy is 2 times I of triangle, Iy of triangle minus Ix of sector. So Iy is 2 times quantity 0.6h cube times h over 12, then minus 0.75 h quantity to the fourth over 8 quantity 2 times 0.5404 minus sine of 2 times 30.964 degrees. So the value of the first term is equal to 0.0368 to the fourth. The second term is 0.007849 to the fourth. So combining, Iy is equal to 0.02815 to the fourth. Then for the polar moment of inertia, about 0.0, it is simply Ix plus Iy. So 0.2224 to the fourth plus 0.02815 to the fourth. So Io is equal to 0.2506 to the fourth. Level 76, for the region shown, compute the moment of inertia with respect to the centroidal x-axis in two ways. So here is the given figure. For the first way, we have to compute the moment of inertia by transferring the moment of inertia with respect to the centroid of the entire area. And that's the first way. The second way is we compute the moment of inertia with respect to the x-axis and call that Ix, and Ix is equal to Igx, or moment of inertia with respect to the centroid, plus area of the entire region times distance, which is denoted Yg square. So for our solution, let's divide the areas into three parts. So this triangle here with dimension 40, 2 times 20 is 40, height is 30, and we have a semicircle of radius 20. So the area of this triangle is equal to 1/2 of 40 times 60. This is 60, 90 minus 30. So 1/2 of 40 times 60, that's 1,200 because that's 60 mm. So 1,200. This area is 40 times 30, 1,200 also. And for the semicircle, pi times 20 square over 2. So that's 200 pi mm square. The location of the centroid of the semicircle from the diameter is 4 times radius over 3 pi, 4 times 20 divided by 3 pi, and that would be 8.488. Again, 4 times 20, 80 divided by 3 pi is 8.488 mm. Then the centroid of the entire region, I call that G, and its distance from the x-axis, YG. For the centroid of the other elements, we'll just read it directly from the figure. So that's YG. So for instance, for the triangle, the location of its centroid from the x-axis is 2/3 of 60 is 40. The location of the centroid of the rectangle is 60 plus half of 30, so 75. And for the centroid of the semicircle, 60 plus 30, 90 plus 8.488, so it's 98.488. So it's readable from the figure, although I'm not putting it to remove the details so that you also think it's you will not learn if the solution is, although this is in video and it is explained, you have to, I will spoon feed you, so there's no learning if that is the case. You can follow, but you will not use your brains most often for that case. So I want you to develop by thinking also. So area is 1,200 plus 1,200 plus 200 pi. So area is equal to 3,028.32 mm square. So by Varignon's theorem, area times yg, 328.32 yg equals 1,200 times 40. As I said, this is 40. 2/3 of 60 is 40 for the location of the centroid of this triangle. 2/3 of the length of the leg from the vertex. 1/3 of the length of the leg from the base. So that's why this is 40. Plus 1,200, the location of the centroid of this rectangle is 60. 60 plus 1/2 of 30, which is 15, so 75. So plus 1,200 times 75, then plus 200 pi times 98.488. So this is 98.488. So solving for yg is equal to 66.00 mm. Then by transfer formula for moment of inertia, I barred x, so rgx is equal to, for the triangle, bh cube over 4 plus area 36 rather plus area distance square. So moment of inertia of the triangle with respect to the centroidal axis is base 40 height cube over 36, remember, plus area 1,200, then the distance between the centroid of the entire area parallel to the x-axis and the centroid of the triangle, which is here, this is 40, so it's yg minus 40. Yg minus 40, that's the distance. Then quantity square. For the rectangle, it is bh cube over 12, so plus 40, 30 cube over 12, then plus area 1,200. Remember, its distance from the x-axis is 75, so 75 minus 66 yg, quantity square. So 40, 30 cube over 12 plus 1,200 times quantity 75 minus 66 square. Then for the semicircle, the moment of inertia with respect to this centroidal x-axis is 0.10976 reduced to the fourth, if you can remember. 0.10976, 20 to the fourth plus area 200 pi times distance 98.488 minus yg, which is 66 square. So computing individually, igx is equal to, in scientific notation, 10 to the 6. So this is 1.0512 plus 0.1872 plus 0.68073 10 to the 6. So combining IGX is equal to 1.919 times 10 to the 6 mm to the fourth. Likewise, the other way is to compute for IX, then equate it to IGX plus area YG square. So by transfer formula. So IX is for the triangle. We have a formula for moment of inertia of a triangle with respect to the vertex here, parallel to the base, which is base 40 times height 60 cube over 4. For the rectangle and for the semicircle, we have to transfer them directly to the x-axis because their centroids do not coincide with the x-axis. Only for this triangle here, where we have an available formula for moment of inertia of a triangle with respect to the vertex parallel to the base, which is bh cube over 4. So Ix is equal to 40 60 cube over 4, then plus for this rectangle here we have to transfer base 40 height 30 cube over 12 with respect to the centroid plus area 1200 distance 75 square, distance of its centroid from the x-axis, so 40 30 cube over 12 plus area 1275 square. For the semicircle, we have to transfer also to this x-axis here, and it is 0.1097620 to the fourth plus area 200 pi times 98.488 square. So Ix is equal to 2.16 times 10 to the 6 plus 6.84 plus 6.1122 times 10 to the 6. Combining Ix is equal to 15.11 times 10 to the 6 millimeter, which is also IGX. Then equate to IGX. Ix is 15.11 times 10 to the 6, and it is equal to IGX plus area YG square by transfer formula. So area is 3028.32 and YG is 66. So 15.11 times 10 to the 6 equals IGX plus 3028.32 times 66 square. So computing, this is the second way. IGX is also 1.919 times 10 to the 6 mm to the fourth. Level 77, for the region shown, compute the moment of inertia with respect to the centroidal x-axis in two ways. So let's solve this in the same manner as level 76 was solved. So this is the given figure. First, for the area, we have area of rectangle minus this triangle here minus this quarter circle. If this is 80 and this is 50, then this must be 30 mm. So for our solution, we have 30 mm here, and the area of the rectangle is 40 plus 50, 90 times 80, so 7,200 mm square. For the triangle, 1/2, this is negative treated, negative 1/2 of 90 times 30, so negative 1,350 mm square. Then for this quarter circle, pi over 450 square, that's negative 625 pi. This is the location of the centroid of the rectangle, which is half of 80 from the x-axis, 40 mm. And it is not shown because I just mentioned it, 40 mm. For the triangle, 1/3 of 30, so 10 mm from the x-axis. For the quarter circle, from the top, from the radius 4r over 3 pi, 4 times 50 divided by 3 pi, and that would be 21.221 mm. So therefore, its distance from the x-axis is 80 minus 21.221, and that is equal to 58.779 mm. So area, therefore, this is the centroid of the entire area, and its distance from the x-axis is denoted by YG as shown. So area is 7,200 minus 1,350 minus 625 pi. In decimal, area is 388 388.6.5 mm square. By Varignon's theorem, to solve for yg, 3886.5 times yg equals 7,200 times 40, as I said, then minus 1350 times 1/3 of 30 is 10, and this is 40, 1/2 of 80. So minus 1350 times 10, and minus 625 pi times 58.779. So computing for yg is equal to 40.933 mm. So we now transfer each of the individual areas moment of inertia with respect to this centroidal g-axis. So this is slightly greater than 40. Remember, this is 40. So the distance between the centroidal axis of the entire area from the centroid of this rectangle is 40.93 minus 40. So IGX is equal to base 90, height 80 cube over 12 for the rectangle. 90 times 80 cube over 12 plus area 7,200, quantity 40.933 minus 40 square. For the triangle, with respect to this axis here, 90 times 30 cube over 36 plus area 1350. Distance is YG 40.93 minus 10 because this is 10. So the vertical distance is between them is YG minus 10. YG minus 10, quantity square. Then minus for the centroidal moment of inertia of this quarter circle, 0.05488 r to the fourth, then area 625 pi, distance 58.779, quantity distance 58.779 minus yg square. So minus 0.05488, 50 to the fourth, plus 625 pi, 58.779 minus 40.933 square. So I hope that you were able to follow this, and especially the moment of inertia with respect to the centroidal axis. So computing in scientific notation 10 to the 6 individually, so we have 3.8463 minus this one 1.35925, and the third one minus 0.96833 times 10 to the 6. So IGX is equal to 1.519 times 10 to the 6 mm to the fourth. For the second solution, let's solve for Ix and equate it to IGX plus area YG square, where Ix is for the rectangle BH cube over 3, because this is the base of the rectangle and it coincides with the x-axis. For the triangle BH cube over 12, it also the base of the triangle coincides with the x-axis, which is the base. But for the quarter circle, we have to transfer moment of inertia 0.05488, radius 50 to the fourth, then subtract it, plus area 625 by distance 58.779 square. So Ix is equal to, for the rectangle, 90 80 cube over 3, BH cube over 3, 90 80 cube over 3. So that's for the rectangle with respect to the x-axis or its base. For the triangle, minus base 90, height 30 cube over 12, 90 times 30 cube over 12. There's no need to transfer. If you want to transfer, then you can, but it's the same as this. Then minus 0.0, so we have to transfer, minus quantity 0.05488, 50 to the fourth, plus area 625 by distance 58.779 square. Distance of this centroid from the x-axis. So computing Ix is equal to 8.0307 times 10 to the 6. So we now combine the values. Then equate this to IGX plus area YG square. So Ix equals Igx plus area Yg squared. Ix is 8.0307 times 10 to the 6. Igx then plus area 3886.5 times Yg 40.933 squared. Solving for Igx, it should be equal to that 1.519 times 10 to the 6 mm to the 4th. So that's it.